Welcome everyone to University of Idaho Extension and University of Wyoming Sheep and Goat webinar series. Would like to thank Dr. Melinda Ellison, University of Idaho Extension sheep specialist and sheep producer, and University of Idaho Extension educator Carmen Wilmore from Lincoln County, and also a dairy goat producer. We're grateful for them for including us in these webinar series. We feel that we've got a good one here today, as we've had previous weeks. Dr. Tom Murphy, I had the privilege of working with at Montana State University early in my career. We both started out there, and Tom has since moved to Hastings, Nebraska, and he is the U.S. Meat Animal Research Center sheep geneticist, heavily involved in NSIP's genetic initiatives, and sheep research extraordinaire. We collaborate quite a bit. He's a good friend of mine, and I'm glad that he would be willing today to work with us on this webinar. And so, Tom, his formal training, I think he's going to give an introduction, but Dr. Murphy, we appreciate you being on today. And again, we'd encourage you to check Facebook at University of Idaho Sheep and Goats, or UW Sheep on Facebook, as these will be posted. There's the YouTube channel for University of Idaho Extension Livestock, and of course the webpage, sheep and goat webpage at the University of Idaho. All right, without further ado, Dr. Murphy, we will turn it over to you, and I'll let you kind of introduce the format, how you'd like to take questions, and we can proceed as follows.
Okay, sounds good. Thanks, Whit. So can you all see my screen here?
Yep.
Okay. All right, well, thanks, Whit, and good afternoon, everybody. As Whit said, my name's Tom Murphy, and I'm a sheep geneticist with the USDA's Agricultural Research Service, working at the Meat Animal Research Center in Clay Center, Nebraska. A little bit about myself. I grew up in Nebraska and got my bachelor's degree in animal science from the University of Nebraska in Lincoln. I stayed there for my master's degree with an emphasis on animal breeding and genetics, and then I went to the University of Wisconsin in Madison to work on a PhD, where my main project actually focused on the genetic improvement of dairy sheep, but I did a lot of other sheep research there as well with our farm flock sheep. After Madison, we moved all the way to Bozeman, Montana, where I was an assistant professor of sheep production at Montana State University for about 2.5 years, working with producers throughout Montana, as well as at the U.S. Sheep Experiment Station in Du Bois. Really exposed me to range sheep production, and at my previous stops, I've been really fortunate to experience the great diversity of sheep production in the U.S., from our intensively managed accelerated lambing systems to our extensive large range lambing outfits and everything in between. But when the opportunity arose, I couldn't pass up coming back home to Nebraska, and I've been here at U.S. Mark for about the last 18 months, where I broadly focus on developing genetic tools for the improvement of lamb and wool production in a variety of different production systems. So today I'm going to focus on how we can use one of those tools called estimated breeding values, or EBVs, to enhance our flock's productivity. So to begin, what traits have the greatest effect on productivity and profitability in commercial sheep operations? In most of our models from scientific literature, we see that traits associated with ewe reproduction and lamb survival have far greater economic impact than traits associated with wool or carcass. That doesn't mean that wool or carcass traits aren't important, but relatively speaking, we can increase our profitability a lot more by improving lamb survival and ewe prolificacy. But before we improve ewe reproductive performance, or any trait for that matter on our operation, we should first ask ourselves, what is the current performance level of my flock? So we need to actually go out and measure the performance of our flock to know where our baseline is. And then we can ask ourselves, what level of performance can my operation or my production environment or my skill set handle? The best indicator we have in the U.S. of ewe reproductive performance from national statistics is our lamb crop. And lamb crop is defined as the number of lambs born per ewe in the eastern states and number of lambs docked per ewe in the western states. So this is a graph of average lamb crop in the upper Midwest states in blue, including Iowa, Minnesota, and Wisconsin, as well as the northern Intermountain West states in red of Idaho, Montana, and Wyoming, and the U.S. as a whole in black. And this goes back to when these surveys first started in 1970. And the first thing you'll notice is there's a tremendous amount of variation from year to year in our lamb crop across the country and within these states. So let's smooth out these lines. And when we do that, we can see that lamb crop in the upper Midwest, again in blue, is generally much greater than average for the Intermountain West and the U.S. as a whole. We also see that the Intermountain West ewe lamb crop has increased above U.S. average for several decades before leveling off, whereas ewe prolificacy in the upper Midwest states improved to about 150% in the early 2000s before fairly drastically reducing in recent years. So the reasons for these differences in ewe prolificacy between these two very different regions of the United States are pretty obvious to us. And it's due to a combination of more prolific breed types that are reared in the eastern United States, their greater precipitation, and generally cheaper access to harvested feeds that can improve ewe reproductive performance. But also when we look at the demographics of sheep production between these two regions, we see that in both regions, the Intermountain West and Upper Midwest, most sheep operators are small, less than 25 head. But in the Intermountain West, we tend to have a greater proportion of much larger operations, 300 to 999 head or 1,000 plus head, and these are pretty few between in the upper Midwestern states. Overall, there's about twice the number of sheep producers in the upper Midwest than the Intermountain West, but the Intermountain West has over 2 times as many ewes because we have these larger, or tend to have larger operations. So the big picture here is that from the first 5 years of this survey, from 1970 to 1974, to our most recent 5 years, the U.S. average lamb crop as a whole has improved by about 10%, or 0.1 lambs per ewe. Iowa, Minnesota, and Wisconsin have improved by about 0.17 lambs per ewe, while ewes in Idaho, Montana, and Wyoming have improved by about 0.2 lambs docked per ewe. But overall, the average lamb crop in the U.S. and each of these regions is still pretty low at 106%, 117%, and 128%. So knowing all of the technologies available to us as sheep producers in 2020, should we be satisfied with this level of improvement over the last 50 years? So we're going to compare this time period to agricultural sectors that are generally associated with the greatest improvements in productivity. So the average dairy cow in the 1970s milked just over 10,000 pounds per lactation. Today, the average dairy cow milks almost 23,000 pounds per lactation, which is a 56% improvement in performance for that trait. The average corn crop in the 1970s yielded about 84 bushels per acre in the 1970s, and today we're at about 170 bushels per acre, 106% improvement. So you all know that there's a tremendous amount of differences between these two sectors in the U.S. sheep industry, and this improvement doesn't come without increased inputs. but I just wanted to show you that there are technological advancements occurring everywhere around us in production agriculture, and some of these could be utilized to some extent in the U.S. sheep industry. And because most of you in Idaho and Wyoming are likely running dual-purpose ewes, I also have here average fleece weight by Intermountain State over the last 20 years. And we see that the performance for this trait also hasn't changed very much either. Now, I know that many of you listening in have taken advantage of various technologies where they fit on your operation, and you do have more productive sheep than average for your region. But for every one of you, there are an equal number of your neighbors that haven't moved the needle much from 1970, and this brings down our average. But before going anywhere, I want to first emphasize that the take-home message is not that every sheep producer in the U.S. needs a 200% lamb crop. This level of production is not easy. We've got increased labor, feed costs, housing requirements. We might have to rear a substantially larger number of lambs on milk replacer. If U.S. sheep production were just about maximizing our lamb crop, we'd all be raising Romanovs. This is the distribution of Romanov used for litter size in our flock here at U.S. Mark, and you can see about 70% of them give birth to triplets and quadruplets, and actually a similar number have given birth to sextuplets than have given birth to singles. But obviously for this increased prolificacy, we have some setbacks. We really sacrifice lamb growth, and these are small lambs that we struggle to find where their light-muscled carcasses can fit in traditional markets in the U.S. And I'm pretty sure no Romanov ewes ever grazed sagebrush before. So the take-home message is we should all seek to optimize prolificacy to a level that fits our experience, production environment, and our other breeding objectives, but we have to know where we stand first. So here's an example of why it's important to match ewe prolificacy to our management system. We've got data from our maternal composite here at U.S. Mark that lambs on pasture, as well as data from polypays at the U.S. Sheep Experiment Station that do lamb in a shed but are put out on summer range shortly thereafter. And we're comparing number of lambs weaned by ewes that gave birth to either singles, twins, or triplets in each of these locations. As you all know, lambs born in larger litters have increased likelihood of dying or being put in the nursery. When we compare twin versus single-bearing ewes, we see that yes, twin-bearing ewes do lose more lambs than single-bearing ewes, but they wean by far more lambs than single-bearing ewes. So if we analyze this as more of an overhead, twin-bearing ewes lose 0.2 to 0.3 lambs per one additional lamb weaned, and we want this number to be less than 1. If you lose 1 or more lamb for one additional lamb weaned, it doesn't make a whole lot of sense economically. And this is what we observe when we compare triplet versus twin-bearing ewes in these low-input lambing systems. Triplet-bearing ewes do, again, wean more lambs than twin-bearing ewes, but they also lose by far more lambs than twin-bearing ewes. So we lose 1.6 to 1.8 lambs per one additional lamb weaned. Okay, so for these low input systems, it doesn't make a whole lot of sense to push for triplet-bearing ewes. Can ewes in higher input systems handle triplets better? Yeah, they can. But this data just emphasizes how we should optimize ewe prolificacy for our operation. So what are some realistic lamb crop goals? Dr. Reed Redden at Texas A&M and others on the Roadmap Implementation Committee put together some expectations for various production systems with the goal of improving the average U.S. lamb crop to 150% by this year, 2020, in order to meet anticipated domestic demand. We know that over half of the lamb consumed in the U.S. is imported. So one way we might improve the amount of American lamb consumed in America would be to offer more of it, to improve the prolificacy of our ewes. But considering last year's average lamb crop for the U.S. as a whole was 110%, I'm not really expecting us to have reached this 150% goal. But nevertheless, we've broken this up, or they've broken this up into different production systems on what we should try to expect for number of lambs born or docked and number of lambs weaned. So for higher input range type flocks, we should strive to have 150% lamb crop born or docked and wean about 130%. For lower input range flocks that might be range lambing, we should strive for 120% lamb crop at docking and wean 100%. And we can see, generally speaking, if you're in a farm flock type situation, either high input or low input, we expect average prolificacy and number of lambs weaned to be much higher. But considering again that the average lamb crop near birth in the northern Intermountain West states is currently 128%, the average producer here or in your region has some work to do. But if you're at or above these numbers and you're comfortable with them, then we can start to focus on things other than improving prolificacy in our flocks. So in order to genetically improve the performance of our sheep for any trait, we need to first understand the basic genetic model. This model tells us that the performance or phenotype of an individual that we can observe or measure is a realization of the genes that individual carries that influences its performance, as well as the environment that individual performs in. So here, if we consider our trait is weaning weight, an animal's phenotype is their actual weight at weaning. We refer to part of the genetic component as breeding value, and an animal's breeding value represents the sum of all of the genes that influence an animal's pre-weaning growth. And there can be tens of thousands of these genes, each having possibly positive or negative effects on performance. All of the other non-genetic effects that can influence an animal's performance, in this case pre-weaning growth, are included in the environmental component. So this represents not just the particular place and time an animal is located, but also things like any pathogens that animal may have encountered that might have negatively affected its performance, the age of that animal's dam, its birth or rearing type, what kind of pre-weaning nutrition we might have provided it. All of these are non-genetic environmental effects that can have both positive and negative impacts on an animal's performance. And we would have this same basic model for all of our traits in sheep production, each with a genetic and each with an environmental component that influences an animal's performance. So as geneticists, we typically focus on breeding value because although both an animal's breeding value and the environment influence their own performance, only their breeding value can influence their future progeny's performance. This ram has his own phenotype. That's the sum of his breeding value and his environmental effect, but his environmental effect is unique to him. It's not the result of heritable effects, so it's not passed on to his future generations. His progeny have their own unique and independent environmental effects that will influence their performance. However, because a breeding value is a genetic effect and an individual passes half of their genes on to their progeny, we expect them to pass, on average, half of their breeding value onto their progeny. So that's why we care about breeding value as geneticists because it's what links the performance of individuals across generations. So what have we learned so far? Well, we know that we can measure an individual's performance, and their performance is influenced by both their breeding value and the environment. However, what we don't know is an animal's true breeding value. As I said, a breeding value is the sum of all of these independent genes that influence performance, and there can be tens of thousands of them. And so we're probably never going to know where all of these tens of thousands of genes lie and each of their independent effects on performance. So what we don't know is true breeding value, but just like anything that we don't know with certainty, we can predict or estimate it. And we refer to this as an estimated breeding value, or EBV. And we calculate EBVs using the performance of an individual and or the performance of their genetic relatives to infer their EBV. However, we have one caveat, and that is accuracy. Just like any prediction or estimation, our accuracy matters. In the case of predicting an animal's genetic merit, our accuracy is dependent on the heritability of the trait, the source, and amount of information that go into our estimate. So if we imagine our true breeding value as the bullseye of our target, we want our estimated breeding value to be as close to this true breeding value as possible. We want it to be as accurate as we can get it. So I mentioned heritability, and most of the time when you look up the definition of heritability, you get some sort of equation that tells you it's equal to the proportion of phenotypic variance attributable to breeding value variance. That's mathematically correct, but that doesn't give you a lot of intuition as to why heritability is so important from a selection standpoint. A trait's heritability is just a number that ranges from 0 to 1. And a more intuitive definition of heritability is that it's a measurement of the degree to which the performance of parents will resemble the performance of progeny. Another slightly different but equally true way of looking at heritability is it's a measurement of the strength of the relationship between an individual's performance and their true genetic merit. We know we can mask performance with environmental effects. So heritability is just a measurement of the strength between an animal's performance and their true breeding value. So here's a table showing typical heritabilities for traits of economic importance in sheep production. We see traits like lamb survival and ewe prolificacy have very low heritabilities, while lamb growth and carcass characteristics tend to be more moderately heritable, and fleece and fiber traits are among the most highly heritable traits in sheep production. So not all traits can be treated equally. We know that lamb survival and ewe prolificacy are among the most economically important traits, but they are lowly heritable, which means that most of the variation in performance for these traits is associated with non-genetic environmental differences among animals. Therefore, for lowly heritable traits, an individual's own performance doesn't represent their own genetic merit or breeding value very well, and an individual's own performance won't represent their progeny's performance very well. So we need to look beyond assessing an individual's own performance and consider more accurate methods of assessing their genetic potential. So I've been preaching the use of EBV in sheep production for several years now, not quite as long as some of our more seasoned geneticists out there, but I've heard my fair share of negative perceptions about EBV, about the National Sheep Improvement Program, from sheep producers across the country. But what these sheep producers don't realize is that any time we use performance records to assess an individual's genetic merit, we are estimating their breeding value. We might think this is my fastest growing ewe lamb. She should be genetically superior for growth than her contemporaries. We are estimating her genetic merit or breeding value for growth using her own performance. Another example is this ram was born a twin. He should be genetically superior for prolificacy compared to those single-born rams. Again, we are using the performance of this ram's dam to assess his genetic merit. We are estimating his breeding value for number of lambs born. The problem is that when we only use a single piece of information to assess genetic merit, our accuracy of that prediction can be very poor. In fact, when we only use an animal's own performance to estimate their breeding value, we can calculate that accuracy pretty easily. It's equal to the square root of the trait's heritability, which can be very low, as I'll show later. So how can we improve how accurately we're selecting individuals in our operation? Well, we do this by considering not just the performance of an individual, but include the performance of their genetic relatives when we estimate their breeding value. And we do this because relatives share some varying proportion of genes in common and therefore share some proportion of their breeding value in common. So going back to our example, we might say, well, this ewe lamb was the fastest growing, but her full sister was only in the middle of the pack. Or this ram was born a twin, but his sire's dam only gave birth to singles. But how do we include these extra pieces of information in an optimum way? How do we determine how much emphasis is placed on a genetic relative's performance? For example, a ram's great-grandsire shares some genes in common with him, but not as much as his full brother does. So shouldn't we place more emphasis on his full brother's performance than his great-grandsire's? The answer is yes. However, fully understanding the models that go into our EBVs requires a good understanding of matrix algebra, statistics, and computer programming. I'm not saying that you can't learn these, because I am from Nebraska and I learned it, but just because you might not fully understand all of the basics that go into the calculation of an EBV doesn't mean that the technology isn't useful to us. Most of us use technologies every single day without fully understanding or thinking about how they work. In the case of the modern planter, we don't think about how interacting with a touch screen sends a coded message to a satellite hovering thousands of miles overhead, which then talks to our GPS unit and results in precision planting. The same is true for EBVs. There's a lot of thoroughly vetted math and theory behind them that ends up with our end product that we can use. So the National Sheep Improvement Program is our source of EBVs in the United States, and it's pretty unique compared to other species. Rather than handling these genetic evaluations separately through individual breed associations, as is commonly done in beef cattle, NSIP is our one-stop shop. Currently, it represents 23 different breeds. There are over 460 individual breeders across the country enrolled in the program, and each year they submit about 14,000 new lamb records. And the program has been growing in recent years thanks to a lot of hard work by those involved in it. The breeds with the most amount of records are here at the bottom, and they indicate our most commercially relevant breeds for many regions of the country. And the traits that we get EBVs on cover really the whole gambit of sheep production, from number of lambs born and weaned to lamb growth and ultrasound, loin muscle and back fat depth, internal parasite susceptibility, and fleece and fiber characteristics. So going back to my point earlier, anytime we use performance records to infer an individual's genetic merit, we are, in essence, estimating their breeding value, but our accuracy matters. So in the example on the left, we have what I refer to as the traditional way of evaluating a ram. we say this ram was born a twin. I think he carries favorable genes for prolificacy. But because number of lambs born is a lowly heritable trait, and because this is a trait of his dam, not his, no ram's ever going to give birth to lambs, our accuracy of that EBV, just considering his dam's performance, is about 15%, or half the square root of the heritability of that trait. So not very good. For a more highly heritable trait like fiber diameter, this ram's own performance for the trait is a decent indicator of his true genetic merit for the trait, and we get an accuracy of about 65%. But for both traits, we can do better. So on the right, I have a diagram depicting the information we might use in the calculation of an NSIP EBV. We're not just going to use the ram's own performance to calculate his EBV. We're going to include the performance of all of his genetic relatives available to us. And again, their respective records are essentially weighted by the proportion of genes they're expected to share in common with this ram. And when we include all of this information, we get much greater accuracies for both traits, but more so for our lowly heritable trait, like number of lambs born. And these are real accuracies that I pulled off of NSIP's website of yearling targhee rams that haven't sired any progeny yet. So as these rams start to sire progeny, their EBVs become much more accurate and can approach nearly 100%. So we've demonstrated that EBVs calculated through the methods of NSIP are the most accurate assessment of an individual's true genetic merit for a trait. But what does an EBV actually mean, and how can we use them on our sheep operations? Well, an EBV is just a number expressed in units of the trait that we measure. So it might be kilograms for weight, centimeters for staple length or scrotal circumference, micron for fiber diameter. So those are our EBVs are expressed in those traits. And they indicate an animal's genetic merit relative to its breed's average. So they can be both positive and negative in value. So for Ram 1 on the left, we see that he has positive and favorable EBV for weaning weight, loin-eye muscle depth, and number of lambs weaned. In this case, decreasing fecal egg count is generally the direction we want to go. So for traits like fecal egg count or fiber diameter that we want to generally decrease, a negative EBV is actually favorable. And we also see Ram 2 on the right here has different EBVs, but we can compare them to Ram 1 and say that we expect Ram 1 to carry a set of genes that make him have a 1.42 kilogram heavier body weight at weaning, or the absolute difference between their weaning weight EBVs. Ram 1 has genes that should make him have a 1.5 millimeter deeper eye muscle, 87% lower fecal egg count, and have a 10% greater lamb crop at weaning. However, these rams have already performed themselves for traits like weaning weight or ultrasound back fat and loin muscle depth. We don't really care about their performance, and furthermore, for some traits like number of lambs weaned, that ram's never going to perform himself for that trait. So EBVs are best used prospectively. And we can compare these two rams as potential sires by assuming that we breed them to a genetically similar group of ewes, and we would expect lambs sired by Ram 1 to be 0.7 kilograms heavier at weaning than lambs sired by Ram 2, or half the difference between the EBVs of these rams, since they submit 1/2 of their genes to their progeny. We'd also expect lambs sired by Ram 1 to have a 0.7 millimeter deeper loin muscle, have 43% lower fecal egg counts, And if we keep ewe lambs out of ram 1 and ram 2, we'd expect ewe lambs out of ram 1 to eventually have a 5% greater lamb crop at weaning. So what else can we do with EBVs? I think one of the greatest uses of EBVs is at a ram sale, and using them as a means of comparing the monetary value of ram or ewe prospects that we're looking to buy. How much are we willing to pay for one ram over another? So going back to our example where ram 1 has a higher EBV for weaning weight than ram 2, we could just make some quick estimates on paper and assume maybe we breed each ram to a group of 30 ewes for 3 straight years, and these ewes wean about 1.6 lambs each, and we sell their lambs at weaning for $1.80 a pound. With that, we'd expect to market over 100 kilograms or 225 pounds more lamb out of ram 1, which would equate in this example to over $400. And we could show similar calculations for greater carcass value if you're selling on a grid, reduced dewormings, and greater lamb crop in retained ewe lambs. Another use of EBV is as a tool to help us better design breeding groups. We've focused on rams so far, but we get EBVs calculated on all of our animals, including our ewes, and we expect a lamb from any ram and ewe crossing to have an EBV equal to his mother's and father's average EBV. So we can use this to structure our breeding groups. We can achieve positive assortative mating. One of the ways we can use EBVs, as I said, is to better structure our breeding groups. We can use what's called positive assortative mating, where we breed our best EBV rams to our best EBV ewes, as well as our worst EBV rams to our worst EBV ewes. This will create really extreme progeny. This will give us lambs with really high EBVs, but we're also going to get lambs with really low EBVs. Another strategy we can use EBVs for is called negative assortative mating, where we breed our best EBV rams to our worst EBV ewes and vice versa, our worst EBV rams to our best EBV ewes. And this is going to create more uniform progeny. It's not going to give us the extreme progeny that we might get with positive assortative mating, but generally speaking, going to give us a more uniform lamb crop. And then finally, we know as sheep producers, we care about improving more than one trait at a time. And NSIP offers multiple trait indexes. These indexes weight individual traits according to their relative economic or biological importance for improving an overall breeding objective for different operations. So, for example, we have the Western Range Index that's utilized quite heavily by NSIP breeders of fine wool and dual-purpose sheep. It puts a really large positive emphasis to increase number of lambs born, smaller emphasis to increase post-weaning weight, maternal weaning weight, which is an indicator of milk production or mothering ability, and it also strives to increase grease fleece weight. This index also puts a small negative weight on yearling weight to keep our mature ewe weight in check, and since we generally want to decrease fiber diameter, it puts a negative emphasis on yearling fiber diameter. So if we were to just go out and select our sheep for grease fleece weight, we know we'd likely improve grease fleece weight on our operation, but grease fleece weight and fiber diameter are positively correlated with one another, which isn't a good thing. It means as we improve grease fleece weight, we expect to get higher fiber diameters or more coarse wool clip. Likewise, if we went out and just selected for post-weaning growth in our operation, that's positively associated with mature weight in our ewes. So we would expect to increase the mature weight in our ewes. So what a multiple trait index allows us to do is identify individuals that have favorable EBVs for fiber diameter and grease fleece weight, or favorable EBVs for post-weaning weight and reduced yearling weight. We also have the Carcass Plus Index that's generally used by terminal breeders, and this attempts to increase both weaning weight and post-weaning weight in those lambs. It also puts a large positive weight to increase loin eye muscle depth, and since we don't want to increase back fat, it puts a negative weight to keep back fat in check. We also have two maternally oriented indexes, one for hair sheep and one for maternal wool sheep, like the Polypay. These two indexes have the same traits but slightly different weights. In these indexes, we put a really large positive weight on number of lambs weaned, a positive weight on weaning weight, and maternal weaning weight, again, an indicator of milk production or mothering ability. But what might not seem obvious is we put a negative weight on number of lambs born. And that's because we don't want ewes to just give us larger litters. We need them to be able to wean all of their lambs. So in this case, a ewe that gave birth to triplets but only reared twins is going to generally have a lower index value than a ewe that gave birth to twins and reared both of them. So I've heard NSIP breeders criticized as just being numbers chasers that don't actually go out and look at their sheep. But remember, EBVs were never developed as the only method of flock improvement. They are another tool in our toolbox to be used in combination with husbandry to improve the productivity and health of our sheep flocks. EBVs aren't going to replace a good nutrition program or a vaccination program. We need to use these in combination with all of our other husbandry practices. A high EBV ewe with a bad bag isn't going to give us high EBV lambs for very long. Similarly, a high EBV ram that only has one testicle and continually fails to his breeding soundness exams isn't going to sire a lot of lambs. And again, we get EBVs on all of the animals that we submit data on, including our wether lambs. So wethers are never actually going to go out and sire any progeny. So EBVs are an effective tool, but they're not our only tool. In conclusion, NSIP estimated breeding values are calculated by optimizing multiple sources of information. With the use of these EBVs, we are more confident on a range of where the true genetic merit of individuals lie, both good genetic merit and bad genetic merit. There is no doubt that genetically superior non-NSIP sheep exist out there. We just can't reliably identify where they lie on this genetic spectrum. So whether you're a seed stock or commercial producer, selecting or buying breeding stock with the use of NSIP EBVs should be the new gold standard in U.S. sheep production. So I just wanted to wrap up by giving you some updates of U.S. Mark, and for many of you that aren't aware of U.S. Mark, an introduction to our program. Mark is actually located on a former ammunitions depot used by the Navy, primarily during World War II. The site actually produced 40% of munitions used by the Navy throughout the war and was still in lower production for the decades after. So if you drive through Mark, you'll see thousands of these bunkers that were used to store munitions. So this is a blast wall. In case those munitions exploded, the explosion would be directed upwards rather than outwards. But they have so much concrete and rebar in them, they're not feasible to remove. So we've still got them all around U.S. Mark. U.S. Mark as a livestock research center was penned into existence by Congress in 1964, and currently we occupy about 34,000 acres, 24,000 of which are in forage, the other being buildings or in row crop production. Technically, U.S. Mark devotes 50% of its resources to beef, 30% to swine, and 20% to sheep. We've got about 8,000 beef cows of multiple breeds. and a feedlot that can hold about 6,400 head. And additionally, each year we produce just under 1,000 litters of piglets. But I know you guys don't care about that. You care about the sheep. Currently, we have 2 scientists solely devoted to sheep research at USMark, myself and Dr. Brad Frecking, but we have many other collaborators both at Mark and around the country. In total, we have about 2,000 breeding ewes and rams. We've got a small flock of Dorset ewes, about 160 currently. These weren't traditionally used by geneticists. They're mostly used as models for metabolism trials, but still they're a really old style Dorset that you don't see around a lot. And it's been a closed flock since the 1960s, originating from some of the original polled Dorset in the country. We also have around 250 Romanov ewes, and Mark was the first to import this breed into the U.S. This is the largest and most genetically diverse Romanov flock in the country. I mentioned the superior prolificacy of the Romanov breed, and for those of you that have interacted with the Romanov, you know they can be a little flighty, to put it mildly. These are some Romanovs that decided they liked it better on top of one of those bunkers. I've never seen any other sheep do that. So again, they have a superior prolificacy that's at a level much higher than most commercial sheep producers want to handle, but they do make good composite crossbred ewes. So that's primarily what they've been used for, but we're also using them to evaluate the biology of ewe reproductive performance in out-of-season lamb production. The Composite 4 is one of those breeds that contains Romanovs. It's a hair breed that's 1/2 Romanov, 1/4 Katahdin, and 1/4 White Dorper. We have about 660 of these ewes that have been selected for improved productivity in low-input pasture lambing systems. We've also got a small flock of Suffolks that we're building up this summer, about 50 head. This will be used as a genetic reference flock to evaluate lamb growth and carcass characteristics. We have about 360 Katahdin ewes that are just out of lambing. Again, this will be used as a genetic reference flock to evaluate ewe and lamb productivity in forage systems. And then we've got about 300 polypay ewes that we're building up. Currently, they're a fall lambing flock, so we're using this as a genetic reference flock to evaluate out-of-season and accelerated lamb production. So I mentioned the concept of genetic reference flocks for the Suffolk, Katahdin, and polypay. This isn't a concept that I came up with, but one the beef cattle geneticists at Mark and sheep geneticists in Australia and other countries use. Basically, it involves having a large group of pedigree recorded ewes that are then bred to influential sires originating from throughout the country. So one of the limiting factors of NSIP currently is that we can only calculate EBVs for traits that producers can measure on farm or ranch, or that are relatively inexpensive to do in a lab. So these are what I refer to as meat and potatoes traits, like number of lambs born and weaned, lamb weaning and post-weaning weight, ultrasound loin muscle and back fat depth, which we can pay a technician to record. We can do fecal egg counts in our own operation or pay to have those samples analyzed at a lab, or for traits like fiber metrology, we can send off samples to a wool lab. But we know that we have a whole other suite of traits that are economically important to us as sheep producers, but really difficult or expensive to quantify on farm or ranch. We've got more in-depth health traits like mastitis, a disease we've been working on a lot, overall immune function, foot health, resilience to respiratory diseases like pneumonia. We've got more functional traits like out-of-season or accelerated lambing potential, milk and colostrum quality. ewe and ram longevity, as well as udder conformation. And we've got lamb performance traits that might be of interest to us, like feed efficiency, lean muscle growth, and eating quality. So by having strong genetic connections with other NSIP flocks, we can measure these traits on populations of sheep here at U.S. Mark and then provide EBVs on them for seed stock and commercial producers to use. So that's what I have for you today. I really appreciate you all taking the time to tune in, and I look forward to sharing research updates with you in the future. And if you've got any questions, I'd take them now.
Thank you, Tom. We got a couple of questions. Our first one is a two-part question regarding NSIP adoption and perceptions. The first part of that, Tom, is the question is, it says you can only collect EBVs on rams if you use a ram whose data already exists in NSIP's program. That is not correct. Correct, Tom? If you can enroll rams and collect data, the accuracy of those EBVs aren't there initially. Once progeny is produced and linkages are made, non-NSIP sheep are brought in that way all the time, correct?
That's correct. So yeah, if you're a new sheep producer to NSIP, you can upload any data that you've had historically. And I recently did this for our Katahdin ewes. We weren't in NSIP before I got here, and I went back and collected all of the data going back to 2006 on them and submitted them to NSIP. What helps strengthen that genetic evaluation is purchasing rams or ewes from other NSIP flocks. But yeah, you can submit old data. You can share rams among different flocks. You can sell your rams to other NSIP flocks. So yes.
Mm-hmm. Oftentimes in Montana, Tom, I think you recall, is certain breeders that are enrolled in NSIP for some diversity, because they have been exchanging rams for a year, from time to time would go outside of NSIP and get some non-NSIP genetics and bring those in and start incorporating data from the progeny that those rams produce. So that's another scenario, correct?
Yes, that is. And, you know, we do see some issues with that when we bring in outside animals. If they have no pedigree or they have no performance records from genetic ancestors, we don't know where they stand genetically. So we have to assume they're right at the population average. But with time, as we enter more progeny data on them, their genetic values move closer to their genetic merit.
And Tom, the second part of that question, again, is more of a perception question, but I think it's important, especially as we think about adoption of NSIP and whether it's the right fit for certain multiplier type flock scenarios. This is more of a statement, but I think it'd be interesting to hear your perspectives. You know, animals currently enrolled in NSIP, you know, there is a perception from, you know, certain breeders who perhaps aren't participating in NSIP, that why would they buy an NSIP ram, you know, if they're inferior to their current level of production? And again, that is very much a perception, but I guess I would ask that question not to criticize any way that people select sheep, but are you truly collecting data on those sheep, or are you just phenotypically evaluating those rams and attributing economic excellence when really you're not collecting a whole lot of objective data? Do you understand that question, Tom? I guess that's a common complaint. Why would I buy an NSIP ram to start getting linked up if I perceive that they're less than my current non-NSIP sheep?
Yeah. Well, that's a difficult thing to assess. I mean, how do you know what's higher or lower performing? So what goes in an NSIP EBV is we're able to account for all of those environmental differences that might occur across ranches. So NSIP Targhee producers in Wisconsin obviously have much more favorable production environments than we'd see in Wyoming. But because of genetic connections between these flocks, we're able to parse out what are environmental effects that influence performance and what are true genetic effects. So EBVs are the genetic indicator. And a lot of times people confuse that with the performance indicator. What we're always interested in as sheep producers is our performance. But when we just go out and buy rams from the guy down the road, we really don't have any idea where they stand genetically, okay, until we start collecting performance records on them. You might say, well, I like this ram, I like some of his ewe lambs, but where's the actual data to show that, and how can you quantify that as that animal being genetically superior?
And you alluded to that, Tom, to some extent. I mean, talking about the accuracy of phenotypic selection on the individual, how less accurate that is. But the other thing I think that we want to make clear is that, you know, phenotypic scoring, if you have a criteria for a certain set of feet in your production environment, you should continue to apply some of those those visual phenotypic selection scores to your sheep. So you are making improvement on those phenotypic things as well. I think I don't believe we're ever proposing an either or, but we do know, as you proposed, that the accuracy of quantitative selection through NSIP just takes a lot of the guesswork out of it and keeps you moving in a direction because you're collecting that data.
Yeah. So what NSIP does well is it gives us genetic merits for our performance traits, but it's not going to tell you that this ram is going to have more wool-blind progeny or lambs with belly wool or poor structure. Those are things that producers do a lot better in culling out of their flock than what an NSIP EBV does for you. And those need to continually be done on all sheep operations, for sure.
Yeah, excellent. Tom, there's one more question. Again, this has to do perhaps with your familiarity with the Romanov breed. Is there any focus on looking at heritability of behavior traits? And we're all aware of the very different behavior Romanovs exhibit.
You know, that's a good question. We're actually trying to look at some of those behavior traits. Romanovs are by far more common in other countries, one of them being in France. They've used them to develop a lot of different composite breeds, and they've actually assessed behavior traits. So they'll like put individual animals in a room by themselves and assess how long it might take them to, say, go to feed or something, and thinking that if they just stand there and shake the whole time and don't get comfortable to that environment, they have poor behavior characteristics. So we do know that behavior is a heritable trait. It's not hugely highly heritable. I'd say more moderately heritable, but we're thinking about ways that we can select those type of sheep that might be a little less flighty. I tend to think that, and I haven't substantiated this, so I'm hesitant to say it, but as we improve prolificacy a lot in some of these really high prolific breeds, maybe that prolificacy is linked with their flighty behavior. I remember in graduate school we had some Burula Rambouillet ewes, and you could always tell when a Burula Rambouillet ewe came through the chute versus just a regular Rambouillet. It seemed they were a lot more flighty and a lot more hesitant to move through working facilities. So yeah, that's a great question, and one we're trying to get a good handle on, and how do you actually measure in a repeatable and quantifiable way behavioral characteristics in sheep.
Tom, as a concluding thought, you know, the push a couple years ago with the Ram Buyer's Guide and NSIP really encouraging Ram buyers to assess their current levels of production. I mean, can it be overstated the importance of knowing what your level of production is and what your objectives are? I feel like that's got to be a primary objective, whether deciding to purchase a ram, is where am I at? Where do I want to be?
That's absolutely true. Before making any breeding decisions, we have to know what our average performance is. You know, maybe you don't need to improve prolificacy or decrease fiber diameter on your operation. But you have to measure it first to understand where you're at.
Well, is there any other questions from any of the co-hosts? I guess while they're thinking of those, I'll put in a plug for next week's conversation. We're going to talk about RAM management in the Intermountain West. Really discuss some nutritional considerations, some behavioral aspects of breeding that we may want to think about, and just a good reminder of how we can get more bang from our buck, no pun intended, when we're dealing with RAM management. So we'll look forward to seeing you next week. Again, we'd encourage you to please fill out the evaluation. Again, our partners both at USDA and our land grant mission, we work very closely together, and that feedback that you provide gives us the ability to continue to do these things. Administrators provide resources when they know that we are constantly improving. So please take some time to give some thoughtful insight there. And Melinda, any concluding thoughts from you?
I have nothing, but I really appreciate you, Tom, for coming on and sharing this information with us.
Yep, no problem. And I
Excellent
didn't
job,
list my
Tom.
email there, but if you guys want to reach out for any other questions, you ask Melinda or Whit, and they can provide you my email.
We sure will. All right. Well, we will see you next week. Again, fill out the survey and have a great remainder of your week.
Thanks, everybody.
Thanks.